Hello, sir. Am I audible? Am I audible? We will wait just 1 to 2 minutes more, then we will start the class.
Good evening, sir. Sure, sir.
Good evening. Uh, everyone. Myself Bindu Sagar Sahu, working as a lecturer in Kendrapada Autonomous College. Uh, I am assigned to teach you your major elective-III course, Supramolecular Chemistry. So, what is the meaning of supramolecular, or how can you define the term supramolecular chemistry? So, particularly, supramolecular means the chemistry beyond the molecules. So when we are discussing about the general molecules, particularly we are discussing about ionic bonds and general covalent bonds or coordinate bonds like that. So these molecules or some molecules they can also form beyond these general interactions. So these types of molecules I can say supramolecular chemistry. This is particularly called as the chemistry beyond the molecules. So in supramolecular system, particularly the molecular components are just like guest and host, or just in your biology or botany, you know about the lock and key theory. There will be a host component and there will be a guest component. When they will together coordinate, they will form a particular types of molecules. So supramolecular chemistry or supramolecules are just like that. But here, the guest and the host components they are held by the non-covalent interactions. So when there will be covalent interaction, I can say there will be a mutual sharing of electron or there will be overlapping of orbitals. But when there will be a non-covalent interaction, it is just like a weak interaction comparing to the ionic interaction and covalent interactions. There will be, we can say, this will be many different types. When I am saying non-covalent interaction, it will be many different types. Here you can see it will be just like it can be sometimes hydrogen bonding also, or it can be sometimes pi stocking also, or sometimes it can be van der Waals force also, or sometimes just like a metal ligand coordination also. So these are the interactions that will exist in a supramolecular compound. And I can say this interaction exists in between a guest and host component. So particularly the idea about the supramolecular chemistry, it is given by Sir Humphrey Davy in 1810, and where he found that a chlorine compound or atom was found to be included in a solid water lattice. That means solid water lattice means we can say this is a cubical shape or a rigid shape of water lattice. In between the water lattice, there will be a chlorine atom that is trapped in between the water lattice. So along with the trapping of chlorine, it will make some non-covalent interaction with the water molecules. So these interactions, it is not strong, just like a water molecule. In between the water molecule, just like an oxygen and hydrogen, they can make a strong covalent bond. But when a chlorine interact with a hydrogen atom of a water molecule, this is not just strong like a covalent bond, but it will be a little bit weaker. Okay. So when a chlorine, it can be trapped inside a water lattice. This types of structure first observed by Humphrey Davy in 1810. Okay, so the first idea it was given in 1810. So it is considered just like a separate discipline of chemistry in 1960. Initially, the supramolecular chemistry considered just like it is a separate uh, discipline of chemistry, just like a nanochemistry, physical chemistry, organic chemistry. The supramolecular also a separate discipline of chemistry. So this supramolecular is highly interdisciplinary. It is linked with different types of or disciplines of chemistry. Particularly, it is linked with the organic and inorganic chemistry, or I can say the physical chemistry also, the computational chemistry, or in molecular modeling also, and along with it is linked with the biological chemistry also. Along with it is also have a linked with nanotechnology or material science also. So next, after this 1810, next different types of compounds, supramolecular compounds. It is given by different scientists. You can see Donald Crumb or Charles or P. Pedersen. They will give him many different supramolecular compounds in between 1960 to 1970, and particularly these all three scientists they will jointly get the Nobel Prize in 1987 for this invention of supramolecular chemistry. So these are the different types of supramolecular compounds. The first one will be a brown ether compound, and second one will be the kryptonite compound, and third one will be this is called just like a guest host interaction. So here you can see this is a macrocyclic ligand. And in between this macrocyclic ligand, there will be a positive potassium ion. For the stabilization of this positive potassium ion, there will be an anion that is present outside the macrocyclic ligand. So the charge factor, here it will be neutral. For this cation, it will be trapped inside this macrocyclic ligand. Here also, you can see this is just like a bicyclic ligand. This is a single cycle, or this part, this will be a separate cycle. So these types of compounds are called cryptanoids. Here also, there will be a potassium ion that is trapped inside this macrocyclic ligands. Or the stabilization of this charge of the potassium ion, to make the stabilize the potassium ion charge, there will be a negative anion that is present outside this macrocyclic ligands. So these particular types of ligands are called crown ether compounds, and these particular types of ligands are called kryptanoids. So in crown ether compounds, particularly in between the macrocyclic ligands, sometimes few amount of oxygen atoms or few atoms of oxygen atoms are present. So you can name just like by counting this numbers 1, 2, 3, 4, 5, 6, 7, 8, just like that. And here there are how many oxygen atoms are present? Here 6 oxygen atoms are present. Or how many carbon centers? 12. So total it will be 18 at the centric centers ring, or I can say 18 crown 6 complex. You can name it just like 18 crown 6. So 6 for the number of oxygen atoms, or 18 for the total centers. Okay. So the property of crown ether complex is little bit different. That means in between the macrocyclic ligands, there will be particularly they will form a just like a cavity, and this macrocyclic ligand it will behave just like a host, and this potassium ion it will behave just like a guest ion. So when a host it will attach to a guest molecule, so there should be some conditions. So if in a host molecule, the specific cavity size it will be driving force to occupy any cation. If the cavity size will be more and the anion will be cation size will be less, then it cannot be trapped inside this macrocyclic ligand. So this cation's cavity size it should be similar or nearly equal to the cavity size of the host. This is the most important condition. But in crown ether complex, this macrocyclic ligands of crown ether complex, they are just like a little bit flexible in nature. That means if this cavity size is this much, so it can occupy the similar size cation, or it can also occupy little bit bigger size cation due to its flexible nature of this crown ether ring. But other types of ligands or other type of macrocyclic ligands, just like in your BSc, hemoglobin, myoglobin, these are the rigid macrocyclic ligands. So what will be the cavity size? They can just trap the particular types of cation. But in crown ether, if this cavity size is this much, they can occupy or they can trap exact size of cation also, or sometimes they can trap also bigger size of cation also. So these types of ligands or macrocyclic ligands are called crown ether complex, and this crown ether complex it can trap some cation in between them. Here also the kryptonites also they can stabilize a positive cation also in between them. Here also you can see a lithium cation. It will also trapped inside this D. So these types of after the invention of these types of macrocyclic complex in 1970, the all the three scientists they will get Nobel Prize for these types of formation of these types of complex. So Jean-Marie Lane, it will be different. He will be defined as the father of supramolecular chemistry, or he's called as the chemistry of molecular assemblies or intermolecular bonds. So this for this invention of supramolecular chemistry, Jean-Marie Lane, they will popularly known as the father of supramolecular chemistry. Okay, so sometimes it is also called the chemistry of non-covalent bond due to its non-covalent interactions. So there are different types of non-covalent interactions. I already told you these types of the types of non-covalent interactions are like that: the van der Waals force, pi-pi stocking, and the metal ligand coordination, like that. So what is the difference in between covalent interaction and the non-covalent interaction? You can see here. Uh, this is general covalent interactions. You can see this is carbon-carbon bond, or this C-chlorine bond and CH bond. These are the covalent bonds. These are the covalent bonds. But here you can see this is a aromatic ring. Here also this will be aromatic ring. So its pi electron, it will lie little bit far away from this benzene ring, or it will lie far away from this aromatic ring. But these pi electrons of this ring and this pi electrons of another ring, they will also make some slight interaction. So these types of interaction, that is not permanent, just like a temporary interactions, I can say this will be non-covalent interactions. So in non-covalent interaction, these interactions are included: hydrogen bonding, pi-pi, CH-pi, anion interaction, and van der Waals force. So further, one by one, we will discuss about it. Okay. So sometimes supramolecular chemistry also, it is told as the guest-host interactions. Okay. Due to, so by doing the guest-host interaction, they will form a stable complex via non-covalent forces. Okay. So in the other names of supramolecular chemistry also, they will sometimes told as molecular devices, machines, or it will be useful for molecular recognition, or it will be useful in nanochemistry also. It will be useful in complexes, emergence of complexes of matter also. So supramolecular molecules have different application in different field of chemistry. So one of the application, most important application, is supramolecular photochemistry also. So when I'm saying supramolecular molecule, there will be a bigger molecule or bigger complex, but in between this bigger complex or bigger molecular complex, small atoms are also present, and these small atoms retain its own intrinsic property. When they will form a molecule or a larger complex that doesn't lose its internal property or intrinsic property. They can also initially they can also show the light absorption, redox activity, other things. When they will form supramolecule, or in the condition when they will also don't form supramolecule, but they will retain its photochemistry properties. So when a supramolecular, we consider supramolecular bigger compound, and in between the supramolecular bigger compound, the small molecules, they can still absorb the light, they can show the redox activity. Then these types of activity or phenomena is just like called as supramolecular photochemistry. So in supramolecular molecules, the small component molecules, they don't lose its photochemistry properties or light absorption properties or redox activities. So you can see here, in supramolecular photochemistry, a supramolecular compound may be defined as an assembly in which each molecular component contributes its intrinsic property, such as light absorption or redox activity. Thus, even a covalent linked system containing a chromophore or spacer or redox center can be regarded as a supramolecule, because each functional unit retains its identity role within the larger construct. So when it will be in a larger form also, it will retain its intrinsic property. When it will be in a micro form also, it will retain its intrinsic property. Am I audible?
Yes, sir.
Okay. Screen visible हो समझते
Sir.
Okay. So you can see here, this is the host complex. This will be a bigger part, and this will be a guest complex, and they will form a supramolecular compound just like that. So this function of the supramolecular compound, it can be behaved in transport system, it can be behaved recognition. Transport system means in transport of ions in our biological process, and it can be used as catalyst also. It can be used for molecular recognition also. Okay, so the upper one will be the formation of a host. We can combine 2 to 3 component, then you can form a macrocyclic ligand just like that. So when there will be a formation of only host, or the basic component of the supramolecular chemistry occurs, we can say this will be a covalent molecule and the interactions are covalent. Okay, but in between this red plus guest and this green complex, host complex, Thus, this interaction is non-covalent types of interactions. Okay, so it may be a weak interaction, but when throughout the lattice these interactions continue, they will make a stable complex throughout the structure, or overall they will make a stable complex. You can see these types of non-covalent interactions and what are their binding force, or what will be their binding energy. So particularly initially I told you the non-covalent interactions are generally weaker than the covalent interactions also, and also it is also weaker than the ionic interactions also. So the range of the covalent interaction is 150 kilojoule mole inverse to 450 kilojoule mole inverse. এটা কাହାର covalent bond ର energy টা କେତେ ରହିବ 150 kilojoule mole inverse to 450 kilojoule mole inverse. When we will discuss about ionic bond, its bond energy will be more than 600, 650, 700, 750, just like that. But when we will consider about non-covalent bonds, the range will be 2 kilojoule mole inverse to 300 kilojoule mole inverse. Yes or no? So this is particularly for ion-ion interactions. So you can see the table, the type of non-covalent interactions, ion-ion interaction, the strength is 200 to 300, and ion dipole interaction, the strength is 550 to 200, and dipole interaction, the strength is 5 to 50. These are the examples. So one by one, we will discuss about each types of interactions. So you can see out of this all the interactions, the ion-ion interaction strength will be more. So out of this all types of non-covalent interaction, always remember the ion-ion interaction strength will be more. It will be in between 200 to 300 kilojoule mole inverse. If we will discuss about ion dipole, it will be little bit less. If we will discuss about dipole, it will be further less, just like that. So you can see here also this value, also the similar values. Okay, so first we will discuss about ion-ion types of interaction. Okay, so you can make a readout also. You can make a reading. Ion-ion interactions are among the strongest non-covalent forces approaching the strength of covalent bond. That means its strength energy, it is nearly nearer to covalent bond strength, and this bond strength is typically in between 100 to 350 kilojoule mole inverse. So ion interaction is just like the interaction in a sodium chloride, Na plus and Cl minus. So we cannot say the sodium plus and Cl interaction, this is just like a non-covalent interaction, but this interaction will be just like a same type of interaction. Same type means which type particularly? How can you understand same type? So when there will be a positive charge, definitely there will be a negative charge, and in between them there will be electrostatic force of interactions. So when I'm saying Na plus and Cl minus, that means Na center is completely positive and Cl minus is completely negative. But in supramolecular chemistry, here when I'm saying ion-ion interaction, that means there will be not completely charged species. These two components are not completely fully charged species. There, I can say this will be a little bit slightly charged positive center. This will be another will be slightly positive negative center. So this ion-ion interaction is similar. So just like NaCl interaction, not exactly sodium chloride interactions. We can see here in figure 1.3a. Here we can see sodium chloride structure. This Na plus, this will be chlorine minus, this will be again Na plus, this will be again chlorine minus. We can see here also. This will be better. You can see this in between the cube, the sodium chloride, they will get just like alternate positions. So after sodium, nearest atom will be obviously chlorine, then sodium, then chlorine, then sodium, then chlorine, just like that. So the sodium will be the positive center and chlorine will be the negative center. The positive sodium plus ion, it will get interact with the chlorine minus ion. That means it will behave just like a positive charge. It will just behave like a negative charge, and there will be electrostatic force of interaction that will exist in between positive center and the negative centers. So you can calculate the force of attraction just by applying the Coulomb's formula. Coulomb's law formula जोटा पढ़ते हो physics से plus 2 physics से Q1 Q2 divided by 1 by 4 pi epsilon 0 Q1 Q2 divided by R square. Yes or no? So this is a ion-ion interaction. This is simply called ion-ion interaction. Okay. Here you can check also. Those the green bulbs are the chlorine center, and these balls are the blue balls are the sodium center or positive center. Okay. So water is a generally we know water is a polar molecule. So in between water, there will be definitely a positive charge. There will be definitely a negative charge. Suppose I am drawing here the water structure. Out of this, in water there are two types of atoms are present. One will be oxygen, another will be hydrogen. So definitely the negative charge will be get partial negative center. It will be the more electronegative atom, it will be get partial negative center, and it will be partial positive center. So in water is a polar molecule with a partial negative charge on the oxygen atom and partial positive charge it will be occupy on the hydrogen atom. And the Na plus ions, suppose we are adding the Na sodium chloride crystal in water molecules. So tell me, the Na plus ion is attracted towards which center of water? Either oxygen center or hydrogen center? So definitely it will attracted towards the oxygen center of the water molecule. So if you add a crystal or solid crystal in a solvent, when there will be a complete separation of sodium chloride occurs, then we can say the solubility will be more. Or if you add a particular type of solid in a solvent, so in a solid, if this complete separation of this charge occurs, that means cation and anion, it will be completely separated. Then I can say this will be here the solubility will be more. Similar cases occurs in sodium chloride. If you adding sodium chloride in water, the Na plus ion it will be attracted or surrounded by the huge number of water molecules, or I can say particularly it will be attracted by 6 water molecules, and they will form a hydration sphere. They will form a hydration sphere like that. So you can occupy 6 water molecules throughout the sodium center, or it can form a cyclic structure compound like that. Yes or no? So the sodium's positive center, it will be attracted towards the oxygen center, and due to here oxygen, they will form a partial negative center. So the water molecule solvent here act like just like a dipole, just like a dipole. And this dipole's negative end, it will be attracted towards the positive center. So when these types of interaction occurs, I can say these are the ion dipole interaction. These are called the ion dipole interactions. So ion dipole interactions occur when an ion, either a cation and anion, it interacts with a polar molecule. So here the polar molecule is the solvent water, and these interactions are directional in nature. So any types of covalent or non-covalent interactions are particularly directional in nature. That means it can attract it towards this atom in this center, or in this center there will be 6 definite centers. There will be 6 definite centers, not more than 6 centers, or these interactions are centers interaction, or the way of interaction of this positive ion and the negative ion are in a particular direction. That's why these are called the directional in nature. Suppose I can say ionic bond. When I'm saying Na and Cl interaction, this is not directional interaction. Ionic bond interactions are non-directional interaction. That means a positive cation, it can attract a huge amount of anions at any direction. But when there will be covalent bond involvement occurs, the particularly this orbital of sodium, it will attract it towards the particular orbital of another negative centered atom. So this when there will be orbital interaction little bit occurs, the directional nature developed inside the molecule. Okay, so it is not strong like that the ion dipole interaction, but it will be also a moderate type or moderate strength type interactions. So if you compare ion-ion interaction and ion dipole interaction, out of them ion-ion interaction it has larger strength, and then ion dipole interaction it will be a moderate strength. Its strength range is 50 to 200 kilojoule mole inverse. Okay, you can check also what are the another examples of ion-ion interaction. One example will be sodium water 6 complex. Yes or no? So these types of complex will form after the decomposition of sodium chloride in water molecule. Yes or no? And the another example will be tris diaza bicyclooctane. This will form a cyclic compound. And the cyclic compound structure you can see here. This one 1.17. This one triaza bicyclooctane complex. Yes or no? So in picture in B you can see this part or this ligand or this macrocyclic ligand, it will be stabilized by this complex FeCN6 3 minus. That means in this complex there will be three positive center, or it will make or generates a 3 plus positive charge. It will be stabilized by FeCN6 3 minus charge. Yes or no? So the overall complex will be a neutral. So in the pictorial picture, you can see this one. This one will be FeCN6 complex, and the rest this part. This part will be tris diaza bicyclooctane ring. Okay. So this deep color ball, these are the nitrogen compounds. These are the nitrogen compounds. Here in pentacyclic ring also, you can see in this hexacyclic ring also, you can see this is the nitrogen center. This will be the nitrogen center, like that. And the rest will be the carbon center, like that. So here the three positive charge, it will be stabilized by these three negative charge. In your book also or in your study material also, these types of pictures are present, but it will be a little bit better. You can see here these pictures in your study material. Tris diaza bicyclooctane, this one. Okay, so these are the examples of ion-ion interactions. They will make ion-ion interaction like that. So another difference in between these covalent interaction or non-covalent interactions are non-covalent interactions. They can be a little bit dynamic or reversible type, or it is sensitive to solvent temperature. If you supply some more temperature, these types of non-covalent interaction they can break also. Sometimes they in a compound also, supramolecular compound also, they can break also, and again they can form also. Yes or no? Sometimes, in a TBP geometry, just like the axial atoms moves towards the equatorial, and the equatorial atoms just moves towards the axial. That means this axial and equatorial atoms. The position is not static; they are dynamic. They are changing every time. So just like in supramolecular chemistry, also some interactions also at a point they exist also, and at a point they also don't exist. So if you can supply more temperature or other conditions, these bonds they can also dissociate also. Okay, so you can read out here on like the rigid NaCl structure. So when I'm saying NaCl structure, this is a rigid structure. They don't show dynamic behavior, reversible behavior, but in supramolecular ion interaction compounds, their structure is just similar like NaCl, but their behavior or properties are different. Here this is a rigid structure, but here the structure is a dynamic, reversible. Okay, it can also break easily. If you supply more temperature, it can also break easily. Okay. Then I already told you about the ion dipole interactions also. In ion dipole interactions, here just like here there will be sodium plus ion. It will behave just like a ion, and another part it will take a dipole. So dipole's negative end, it will make an interaction with the sodium atom. So here the dipole is the solvent or the dipole is the water molecule. Okay, fine. So this is a dipole and this is a ion. So these types of interactions are called ion dipole interactions. Okay. So if you surround it by 6 water and it will form a just like a hydration cell. It is called just like a hydration cell or it is just like a hydration sphere. If you surround 6 water molecules around a Na plus ion, it will form just like a hydration sphere around a Na plus ion. Here you can read out also. This leads to the formation of a hydration cell such as Na water 6 plus, just like the structure. Okay, so instead of water molecule, suppose you can imagine another crown ether complex. This complex is called 15 crown 5. 15 crown 5. In figure, you can see also what is 15 crown 5 complex. And this one, this complex is called 15 crown complex. So why 15? You can count its atomic center, oxygen center also, carbon center also. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. Just like that. So the total center will be 15. And how many oxygen centers? 5. 1, 2, 3, 4, 5. That's why its naming is just like 15 crown 5. So in between a 15 crown 5 complex, a sodium plus ion is trapped. So here the oxygen atom, it will get a partial negative charge, and this partial negative charge of this oxygen atom, it can also interact with a sodium atom that can occupy or trap inside this macrocyclic ring. Yes or no? So these types of interactions are also called ion dipole interactions. So here ion is Na plus and 15 crown 5 complex will be a dipole. Okay, so these are the larger ring shaped molecules with several oxygen atoms strategically positioned. Okay, তার মানে oxygen atom রা কোন দেব? They will be in a fixed direction, just like a pentacyclic ring. They will interact in a 5 direction with the sodium. You can read out here also. When a metal cation like sodium or any potassium ion enters into the cavity of crown ether, the lone pair on the oxygen atoms coordinated to the cation. So due to the presence of lone pair, the oxygen atom, it can get an easily a partial negative charge due to its electron density or lone pair electron density. So this results to make a high stable post-gas interactions. Okay, so here also it is forming a stable complex, but the stability is little bit less comparing to ion-ion interaction. And when a complete ring, it will attach to a central metal atom. They also form a chillet effects. So particularly in coordination chemistry, chillet effects are creates when they will form a cyclic ring after the chillation process or after the interaction. So when there will be a chillation process occurs, when there will be formation of ring inside the structure occurs, they will get a extra stability. So this is called chillet effect. So particularly the chillet effect is creates due to increase in entropy. When entropy will increases, it makes favorable for gives energy or it makes favorable to create more negative gives energy. When it will make more negative del G value or gives energy, the process will be more feasible. Okay. So the stability of such post-guest interaction in iron dipole interaction molecules, it occurs due to these following regions. In the third case, you can see the entropy loss is less significant and due to presence of chillet effect. And again, in macrocyclic structure, the crown ether complex, they will make a better non-covalent interactions. So just like these types of synthesized compounds also in biological processes also, valinomycin in antibiotics, they will also form these types of complex with some ions inside our biological process. So these types of antibiotics, they can also make ion dipole interactions with some positive cations in our body through the membrane. Just like it can transport this antibiotic, it can transport the potassium ion through this interaction, ion dipole interactions, or sometimes by hydrogen bonding interactions. So when you need to transport or make an interaction of positive ion, definitely the interaction is ion dipole. When you are making an interaction, just like HF, water, or just like other compounds, hydrogen H2, hydrogen sulfide, their hydrogen bond interaction occurs. Am I audible?
Yes, sir.
Okay. Okay, so you can see here the valine structure, they will form a cyclic ring just like that. Three means these types of three cyclic rings are present. They will cover just like that. Okay, so just simply remember this unit. Till times this unit, it will make a valine antibiotic. It's not necessary to draw this exact structure, these types of structure in exam, but you can represent like that. So the third types of interaction is dipole-dipole interactions that will arises when two polar molecules align in such a way that one of the positive end, it can interact with the negative end of the another molecule, or another molecule's negative end, it can interact with the positive another of one dipole. Yes or no? That means if you can consider just like there will be a dipole, one having positive end, another having negative end, and another dipole, they also have a positive end, they will have a negative end. So for dipole-dipole interactions, one of the dipole's negative end, it will be most close to the positive end of the another dipole. Similarly, another dipole's negative end, it will be most close to the other molecule's positive end. So when there are different dipole ends are present, they can make a interactions. This interaction is called dipole-dipole interactions. And these dipole-dipole types of interactions are generally weaker than the ion-ion or ion-dipole interactions. But they still have a significant role, or this interaction, it may be weaker interactions, but if we are taking the overall molecule strength, so definitely the dipole-dipole interaction has some impact on molecular strength, crystal packing, and solubility of the compound. So the exact value of this dipole-dipole interaction range is in between 5 to 50 kilojoule mole inverse. Or it is also reversible in nature. It is also dynamic in nature. Okay, so like that similar thing. So dipole-dipole interactions are two types. First type is, remember, parallel alignment of like poles, which is relatively straightforward. You can see here first types of dipole interaction. Wait just a minute. Here you can see here dipole-dipole interaction in acetone. This is just like a parallel alignment. You can see here acetone molecule. You can see acetone molecule. Anyone have any doubt? You can see here acetone molecules. This is carbon end, this is oxygen end. Definitely the oxygen will be partially negative, carbon will be partially positive. In another molecules acetone also, this will be carbon end, this will be oxygen end, and this will be a negative end, this will be a positive end. So these lower acetones, oxygen atom, or its negative end, it will make a interaction with the carbon end of the another oxygen, a carbon atom. Here, this types of interaction. এই acetone molecule carbon end এই acetone molecule oxygen end সହିତ ଗୋଟେ interaction create କରୁଛି. So this is a dipole. Here this carbonyl group it will form a dipole also. Here this carbonyl group it will also form a dipole. So the negative end of oxygen it can make interaction with the carbon end, which is a positive center. Which is a positive center. Here also this oxygen's negative center it will make an interaction with this carbon center. Yes or no? So these types of interaction is called dipole-dipole interaction, but it is the alignment is here parallel type. This dipole and this dipole is in a parallel position. Yes or no? You can read out here. The type 1 is parallel alignment of like poles or positive to negative, which is relatively straightforward. Another position is type 2 is anti-parallel or edge-wise alignment. Okay. Anti-parallel or edge-wise alignment. Here you can see this alignment will be called anti-parallel, or it is looks like just like a perpendicular types of alignment. You can see if you consider this is a straight line, the molecule is coming just like that. So these types of alignment is called anti-parallel alignment. That means this acetones, this carbon positive end, it will make interaction with this oxygen. So these types of interaction is called anti-parallel alignment or a edge side alignment. And here this type of alignment is called parallel type alignment. You can check here. Okay, so this one is parallel type 1. This one will be anti-parallel type or edge side interaction. Okay, but both of these are dipole-dipole interactions. Okay, so you can make a more reading that in a real world, carbonyl compounds such as acetone in the solid state, acetone molecules align such that the positive hydrogen atoms on the one molecules it can be nearer to the negative carbonyl oxygen of the neighboring molecules. So this type of dipole alignment helps to make the overall molecules high boiling point and gives its molecular size. So we cannot ignore these types of non-covalent interaction or weak interaction, because these types of interactions has a great impact on the boiling point of acetone. So acetone it is showing a little bit more high boiling point, and this higher boiling point it is due to the presence of this dipole-dipole interactions. Okay, so no doubt this dipole-dipole interaction it is less weak, it is less, it is strength is less comparing to ion dipole or ion-ion interaction, but it has an impact throughout the molecule or overall on the molecule. So in supramolecular chemistry, generally dipole-dipole interaction are not always the primary driving force, but they have a role inside the molecule to make the interaction, the overall stronger interaction of the compound. So when I am discussing about dipole-dipole interaction, if the molecule's boiling point increases, not only dipole-dipole interactions are involved, there may be other types of interaction, hydrogen bonding or ion-ion interaction also present, but it has some impact. It's not the primary driving force or primary interaction, but due to the presence of this interaction, it has some impact, or due to this type of interaction, its boiling point will be little bit more. Okay. So if you discuss about these three types of interaction, ion dipole and dipole-dipole interaction, definitely the stronger interaction will be the ion-ion, which is comparable with the covalent interaction. These are the conclusion. If you discuss about these three types of interactions, definitely the ion-ion interaction it will be the strongest interactions. And after that, ion dipole, and thereafter dipole-dipole interaction. So despite being the weakest directional interaction, I'm discussing about the dipole-dipole interactions are useful for bringing species into alignment. So definitely when there will be interaction, it may be weak interaction, but due to this weak interactions also, the molecules make a proper alignment. Okay, or the molecules become little bit directional in nature. Okay, so when there will be absence of interaction, and definitely, and there will be, I can say there will be no directional nature in exist inside the solid lattice or space lattice. But when there will be definitely interaction, definitely there will be little bit alignment of the molecules, or the molecule it will remain in a proper position, just like it maintaining proper direction. So when there will be presence of the interaction, definitely the directional nature of the compound it will increases. Then we will discuss about hydrogen bonding. You know more about hydrogen bonding in your graduation courses also. So when I am told about hydrogen bonding, definitely one of the atom must contain hydrogen. One of the most atom contain hydrogen. That doesn't mean that H2 molecule can show hydrogen bonding. So hydrogen it can show the hydrogen bonding tendency when it will attach with another atom. That's electronegative difference is more than hydrogen. Or that's electronegative value, it makes a larger difference from hydrogen. So when in a diatomic species, when a in a diatomic species, the A atom, if the A atom has larger electronegative value, it will get partially more electronegative, and it will get partially more more electropositive. So when the electronegative difference will be more, the bond will be more polar. The bond will be more polar. So definitely hydrogen bond it will be created by the atoms when the polarity will be more in between them. So ତାଙ୍କ ଭିତରେ polarity ଟା କ'ଣ ଥିବ ଅଧିକା ଥିବ. So particularly hydrogen atom it will make hydrogen bonding, particularly oxygen atom, nitrogen atom, and fluorine atom. Not with the other types of atoms, carbon, sulfur, selenium, just like that. Because the electronegative difference in between hydrogen and these atoms are very, very less. So it will form hydrogen bond with a highly electronegative atoms. When it will interact with the highly electronegative atoms, these bonds will be more polar. When these bonds will be more polar, one of the center will be more positive center, another center will be more elective electronegative center, and another atoms Ha or another atom similar types Ha, this will be positive center and this will be a negative center. So this negative center it can also make an interaction with this positive center. So the hydrogen bond is particularly, I can say, it is a special type of dipole-dipole interaction. So this is a dipole, just like this is a positive center, this is a negative center. Here also this is a positive center, this is a negative center, and this negative center atom it will make an interaction with this positive center. So it is one of the special type of dipole-dipole interaction. But particularly here in a molecule, the hydrogen atoms are involved. That's why this is called hydrogen bonding. This is called hydrogen bonding. So hydrogen bonding, it can create with the specific atoms just like oxygen, nitrogen, and fluorine that can possesses the lone pair of electrons. So it can exist in different form. We can see here this is a DH dotted A. So this dotted form is the dipole interaction. This dot or dashed form, this is the dipole interaction in between the A center and the DH bond. So in DH, D is the donor atom. That means D will be the more electronegative atom. It may be nitrogen or oxygen and fluorine. And A is the acceptor atom. Here it must have a lone pair. So the positive center of this side component, it will interact with the negative center of the another molecule. So these types of hydrogen bond, they can also form. So A is the acceptor atom, which must have a lone pair. D is the donor atom, and H is the hydrogen atom. So the strength of hydrogen atom is always in between 4 to 120 kilojoule. Okay. So this variation in hydrogen atom in their strength or in their typically energy range, it occurs due to several regions. You can remember these three regions or three different factors. One is the electronegative or donor atom and the acceptor atom. If the electronegative amount of the donor and acceptor atom is more, or electronegative amount is more, then it can more strongly hold this hydrogen atom. That means if the electronegativity of this donor and acceptor atom it will be more, the more will be the strength of the hydrogen atom. Second thing is that the geometry of the bond, particularly the linear bonds are generally stronger, or mostly the orbital overlapping is called linear overlapping. You can remember in molecular orbital theory also, when we are interacting the orbital, we are saying LCAO, linear combination of atomic orbitals. So when there will be little bit orbital combination occurs, I can say this interaction will be linear type. Third thing is that solvent is the most important factor also. So in to make throughout a hydrogen bonding, we need to take a solvent also, and the solvent must have the polar in nature. So you can take water also is a solvent. The role of solvent is also important to strengthen the hydrogen bond. So we can say also, according to their strength, they can also divide it into three types: strong hydrogen bond also, moderate types of hydrogen bonding also, or weak types of hydrogen bonding also. So particularly strong type of hydrogen bond, it will form with the in presence of the more electronegative atom, just like fluorine, which is partial covalent in nature. You can see fluorine H and another fluorine atom. This will here this fluorine will be donor, this fluorine will be acceptor. Yes or no? So this positive and hydrogen it will make interaction with the fluorine. So why this strength is more? Because the involving or interacting electronegative atoms, electronegative value is very high. So you can remember, or you know also the electronegativity of fluorine atom is 4.0. Then second type of interaction is called carboxylic acid interactions, or in organic compound. And these interactions are moderate types of interaction. So you can search here also moderate type of interaction also. Okay, here it's not present, but later we will discuss. Okay, carboxylic acid with the interaction ଟା ହବ ତାକୁ କଣ କହିବା? carboxylic acid with the dimer formation କରିବେ ତାକୁ କହିବା moderate type of interactions. And the third or weak type of hydrogen bonding interactions are just like one of the atoms CH atom it will interact with another atom's oxygen, and one of the atoms CH atom it will interact with the pi electron of another atom or another molecule. This according to their strength, we can divide hydrogen bonding into three types. One will be strong type, another will be moderate type, another will be weak type. So out of these three, if someone will ask which one will be stronger, so definitely these types of when the chlorine atoms or oxygen atoms are involved, they will form a strong type of hydrogen bond. So you need to remember these types of hydrogen bonds. So the detailed description about these types of compounds are mentioned here. So these types of structure is called here also you can say linear structure, or this is called bent or bifurcated bonds. So this interaction it may occur in linear direction also, or sometimes it can occur in a bent direction also. So when there will be bent interaction occurs, we can say this will be bifurcated interaction. Or sometimes it can also make the linear interactions. But out of these two types of interaction, definitely when there will be linear interaction occurs, the strength will be more and the bond will be more stronger. Or when there will be bend interaction occurs, definitely it will be a hydrogen bonding interaction, but this interaction it will be moderate type of interactions. Okay, so we need to see these pictures 17 C D E. This is this one A. This will be linear interactions, just like chlorine, hydrogen, and again fluorine. And this will be a band type interaction. Fluorine, hydrogen, and again fluorine. Okay. And these are the different types of other interactions. This is called donating bifurcated interactions. That means this will be a donor atom. It may be nitrogen, oxygen, and chlorine. This will be a hydrogen atom. Then another here there will be another acceptor atom, and the acceptor atom is also a electronegative atom. It can be oxygen, nitrogen, and chlorine also. So these types of structures, this is called donating bifurcated structure. Bifurcated means it is just like this is forming a one angle, and it can form two angles with respect to the donor atom. This is called donating bifurcated. And at this D, D is called accepting bifurcated. You can see here. The naming is wrong. Actually, ABC. What we can see here, this is accepting bifurcated. And this is called trifurcated. This will form in three direction. Okay. And the last one, this is called three center bifurcated. This will be three center bifurcated. It will form a cyclic ring just like that. Three center means this is one sector, this is one center, this is one center. One, two, three. This is called three center. This is also called one, two, three. Just like B2C6. Diboron is the formula way. Diboron B2A6 now structure boron, hydrogen, boron, and here also hydrogen, here boron atom, here hydrogen, here also hydrogen. So these three atoms, this is called as D center two electron system. Two electron system is separate thing, but this is a three center system. One, two, three. Here also. One, two, three. This is called three centered bifurcated. Bifurcated means it is fructated in two directions. In this direction also, in this direction. It is trifurcated this system. This direction, in this direction, in this direction. So these are the various types of hydrogen bonding geometries. So you need to remember one by one different types of interactions. Okay. Then again, this is called primary and secondary hydrogen bonds. Okay. So different types of we will discuss about different types of primary and secondary hydrogen bond interactions. So the direct DHA interaction, this is called primary hydrogen bonding interactions. So the secondary interactions are the electrostatic interactions or repulsions between adjacent groups, often influencing the binding. So one by one, we'll check what is primary interactions or what is secondary interactions. So in example, we can see both primary and secondary interaction, they are exist in between the molecules. So here we can see in 18.A, the secondary interactions providing interactions between neighboring groups in DD or AARI. So in a cluster compound, we can see this is the donor atom, this will be donor atom, this will be hydrogen atom, this will be hydrogen atom, this will be hydrogen atom. And in another cluster compound, we are taking the acceptor atoms that is connected to the end of the molecules. So here, this hydrogen, it will make an interaction with this A molecule. And also here, this hydrogen, it will make the negative interaction with this types of molecules. So these types of dotted interactions in the side interactions, or this is called these types of dotted interactions in between different poles, they will create a attractive interactions. They will create a attractive interactions. If the similar atoms are present in this direction, they will create a repulsive interactions. So when we are taking DDD and AARI, so we are generally getting they accept attractive interactions in between the this cluster compound and this cluster compound. But if you take DAD configuration and ADA configurations, you are getting both attractive force also, or you are getting both, along with you are getting also repulsive interactions also. So in secondary type of hydrogen interactions, if you are taking or two types of different molecules or two types of different groups, in one group, the arrangement is TD types. That means donor, donor, donor atom, and another cluster molecules, acceptor, acceptor, the same direction or in a parallel direction. Then they will create interaction in between the two groups, and this interaction is only due to the attractive interaction. So you can see linearly also, you can see sideways also. In both cases, they are making the attractive interactions. But if you take one of the cluster compounds DAD interaction and another compounds ADA interactions, you are getting both attractive interaction along with the repulsive interactions. Okay, you can see here secondary interaction providing attractive interaction between the neighboring groups in DDD or AARI, and repulsions from mixed donor acceptor array when the interaction is ADA or DA type interactions. Okay, so you can see here, here we are getting only attractive interaction, you are getting both attractive and along with the secondary repulsive interactions. So these types of primary interactions and hydrogen bond or secondary hydrogen bond interaction, these are also find down in our base pairs or DNAs also. So you know, these amino acids ATGC, they will make hydrogen bond in between them. Sometimes they will make a two hydrogen bond interaction, sometimes they make three hydrogen bond interactions. So these types of interactions also, sometimes they will make primary and sometimes they will make secondary interactions also. So you can see clearly here these types of double stranded DNA. You can see AT, adenine, T means thymine, guanine, cytosine, C means cytosines. So one of the strands adenine, you can see another strands thymine. They will make two hydrogen atoms. They will make two hydrogen atoms. One of the atoms guanine, another atoms cytosine. They will make three hydrogen bonds. Okay, so the GC, guanine and cytosine, they will form three hydrogen bonds, and adenine, thymine, they will form two hydrogen bonds. So these types of hydrogen bond also, they will involve both primary as well as secondary interactions. Okay, so these types of primary and secondary interactions, they can exist both in normal compounds also and in bases also, in biological compounds also. Then we will discuss about the pi-pi interaction compounds. The pi-pi interaction compounds. In pi-pi interaction compounds, it will be different types, just like cation pi interaction, anion pi interaction, and pi-pi stocking interactions. So we can consider three different types of cation pi interactions, pi-pi interactions. That means one component's pi electron density, it can also make a interaction with another component's pi electron density. Yes or no? Or it may be the interaction may be the positive charge center. It can make a pi interaction, or a negative anion. It can also make a pi interaction. So first we will discuss about the cation pi interaction. So particularly this cation pi interactions, it occurs in between a cation, just like potassium plus sodium or a silver metal, with the pi electron cloud of the aromatic systems. So you can see here these types of interactions, cationic pi interaction here. You can see this cation, one of any cation, it will make a interaction with a pi electron cloud of this benzene ring. Or you can take a NH4 plus ion, and this NH4 plus ions positive charge, it can also make a interaction with the pi electron system. Popularly, particularly the ferrocene compound in organometallic chemistry, ferrocene compound or sandwich compound. A iron atom, it will be trapped inside the two cyclic ring, cyclopentadiene ring. So this will be Fe2 plus, it will be C5H5 minus. Here this ring will be C5H5 minus. That means this F is positive charge, iron a positive charge. It will make interaction with the pi electron cloud system of the cyclopentane ring or cyclopentadiene ring. In Jesus salt also, this in Jesus salt popularly in organometallic chemistry, this platinum's positive charge, it can also make the interaction with the pi electron cloud of this alkene complex, like that. So these types of interaction is called cation pi interactions. This is called cation pi interaction. You can write these all types of examples. Okay, that are not exactly available in your book, but you can find out in Google or other internet sources also. So the strength of this interaction is 5 to 80 kilojoule mole inverse. Okay, so it will be a strong enough, or it will be just like its energy. It will be a range of the energy, just like a iron dipole interaction also. So these types of interaction, it is always found in most of the biological systems also, or synthetic receptors means in the chemical synthetic compounds also. Or simply you can uh, write this potassium ion interaction with a benzene ring. Okay, this is just like a cation interaction with a pi system. You can see here, this is a benzene ring compound. These are the pi electron clouds. So these pi electron clouds, it can be get attracted towards a positive center also. Or I can say the negative charge, it will be direction is just like the outside towards the ring. That's why this direction is just like that. Or before also in benzene, the pi electron density, it will be present on the above the plane or below the plane. Okay, the second types of interaction is anion pi interactions. So here a anion is making a interaction with a pi electron cloud. But here the difference is that here the pi electron cloud of this cyclic ring, it will be just like a electron deficient aromatic ring. That means in previous case, we are taking the cyclic ring which is not electron deficient. The cyclic rings pi electron density is more. This is electron rich aromatic rings. But in anion pi interaction, we are taking the electron deficient aromatic rings that can make interact with a anion, and they can form a anion pi interaction types of compound. So you can see here this anion pi interaction compounds here, just like a perchlorate compound ClO4 minus compound, and here we are taking this cyclic ring in hexa substituted fluorine in benzene. These fluorine atoms particularly, they will extract or withdraw the pi electron density towards itself. So in between the ring, there will be an electron deficient nature is observable due to this withdrawing groups or fluorine groups present in the substituted position. So now this ring is a electron deficient ring. So when it will be electron deficient ring, it can interact with an anion. So these types of interactions is called anion pi interaction. This is called anion pi interaction. Okay. So generally it seems just like this is a negative center, and here also this is a negative center. They will repel each other. But here, particularly this electron density, it's not spread out, just like a benzene ring electron density, because this electron density, they are withdraw towards this fluorine center. That's why this electron density here decreases. So this is electron deficient ring now. This will behave just like a electron deficient ring. This electron deficient rings, it can also make interact with a negative charge. So this type of interaction is called anion pi interactions. So you can see here, just like electron deficient aromatic rings, it can make interact with perfluorinated anions. These are the example of anion and pi interaction groups. Okay, and the energy of these types of anion pi interactions are 1 to 10 kilojoule mole inverse. So mostly the anions are the fluorine, chlorine. They are interact within the pi acidic ligands. So pi acidic ligands means you can just understood just like the ligands or rings which is electron deficient in nature or electron poor aromatic rings. These are called electron poor aromatic rings. Okay, interactions or this is called pi stocking interactions. So this is popularly present in graphite structures. So graphite, they will form different planes, just like benzene ring. They can form huge number of planes, just like benzene ring. So here you can imagine, just like this is here, not only one benzene ring is present, is a lot of benzene rings are present, but it is present in a plane, and here also another plane is also present. So in between these two planes, one of the planes pi electron, it will also get attracted towards another rings uh, pi electron center. So these types of interaction is called pi interactions. So these types of pi interaction, it is also two types, just like face to face interaction here also, or this is called edge to face. These types of interaction generally observed in graphite. This is called pi stocking. In this type of interaction, this is called T-shaped interactions. T-shaped interactions, or I can say edge to face interactions. So you can see here, these are the examples: face to face, edge to face. Okay. So these are generally observed in graphite. Okay. Here you can see what are the quadruple moments of this ring. So simply, if you consider a benzene ring, the negative charge will be above the plane and the above the plane of the molecule, and the negative charge also on the plane of below the plane of the molecules. The arrangement of the charge will be just like that, because here pi electron density is present, here also pi electron density is present. But if you take a electron deficient aromatic ring, just like CF6, the positive charge center, it will be above the plane, and the positive charge center also below the plane, and on the plane there will be negative center. So if you can take a negative charge, just like anion and pi interaction, this you can take a negative charge F minus, it can easily interact with that electron deficient ring of the C6F6, because in C6F6 the positive charge, it will be on the plane of the molecule or below the plane of the molecule. But if you take simply benzene, you can say the pi electron densities are present on the plane of the paper or plane of the molecule or below the plane. But if you take the C6F6, just like electron deficient molecule, the charge distribution, it will be changed like that. If the charge distribution is changes, the positive part, it will be easily can make interact with the negative anion. So these types of interaction we can say pi anion interactions. So this pi cation interaction, or it may be pi anion interaction, these are called ion induced dipoles interaction particularly. This is called ion induced types of dipole interactions. Okay, so these are all types of some types of few types of non-covalent interactions I will teach you. Okay, if you have any doubt you can ask, or if you have any other questions also you can ask. Okay, so in next class we'll discuss about what is about the van der Waals forces, London forces, or dispersion interactions that are also present in the graphite or other types of molecules. So you can see here the structures also. Pi interaction structure देख दिया. Here the anion pi interaction. This is cation and pi interaction. This is water molecule. So water molecule, it can form hydrogen bond also. So I can say one of the water molecule, they can form four hydrogen bonds. In this direction, they can also form a hydrogen bond. In this direction, they can also form a hydrogen bond. Here also they can form a hydrogen bond. Here also they can form. So one water molecule, they can form four hydrogen atoms, just like that. So after the formation of hydrogen bonds in water molecule, actually they will form a rigid C-type structure like that. Rigid C-type structure like that. Yes or no? So particularly this type of rigid structures, they will form in the solid form of water, particularly in ice. So whenever they will form this type of rigid structure, there will be a larger empty space in between the water molecules. That's why water in ice form, it has less density. So it can float on the liquid water. So generally, if you consider any compound solid form, liquid form, and gaseous form, definitely the solid form has more density comparing to the liquid and gaseous. If you go from solid to gas, generally the density will decreases. If you go from gas to solid, generally the density increases. But in ice or in water, in solid form, there will be little bit exception, and this exception arises due to the hydrogen bond. So in the water, in its solid form or ice form, they will form just like a rigid sheet-type structure like that. So when they will form a rigid sheet-type of structure, there will be larger empty space in between them. So when in a particular structure, the empty space will increases, definitely the density will decreases. So in ice, that's why ice density is less. That's why it can float on the liquid water. Okay, these are the different types of hydrogen interactions. These are the overall hydrogen bonding interactions and their energy. This is two different types of dipole-dipole interaction. This is parallel alignment. This is opposing alignment or anti-parallel alignment. This is ion dipole interactions. So here ion is sodium plus and dipole is water molecule. Here ion is Na plus and dipole is crown ether complex. Okay, this is organic compound. Here you are taking the ligands bipyridine. You can see here ruthenium is 2 plus and this bipyridine is the dipole here. And this is ion-ion interactions. Efficiency 3 minus, and this one is tris diaza bicyclooctane. This one, and overall this charge will be 3 plus, and here efficiency is 3 minus. The overall charge will be 3 minus. The 3 plus charge, it will be neutralized by the 3 minus charge. Okay, so if you have any question, you can ask.
Uh, Sir, may I ask tomorrow?
Okay, okay. No issue. Okay, thank you. So for supramolecular chemistry, you can also follow these types of books also. The founder has also a book, for another book, J.M. Lane, book of supramolecular chemistry. Or you can also read it from this popularly book. The writer is Asim K. Das. And you can also follow Kalsi and Kalsi book also. But this will be easy, Asim K. Das. Okay, thank you.
Thank you, sir.